You may have noticed something happen when we sketched solutions to an autonomous differential equation. For example, just the differential equation dy dx equals y. Right? This has an equilibrium solution at 0, and solutions that start above y equals 0 sort of swoop upwards like this. And when we drew more than one of them, they all kind of ended up looking generally the same shape. And it's hard to know without actually solving the differential equation if these are exactly the same shape, just shifted around, or if they somehow differ slightly. But we can use our general framework for working with differential equations to see if these are the same shape. So let's suppose that we have a differential equation and we have some solution to the differential equation. Our idea is maybe if we just slide this solution to the right or left, we get another solution. So we know that this solution phi, this is a Greek letter phi, we know we have a solution, or we're supposing we have a solution. And the question that I want to ask is it still a solution if we translate it horizontally? And remember, to translate a function horizontally, you add or subtract some constant on the inside, like this. So is phi of x minus c a solution? Well, let's see, how can we check if a function is a solution? To check if a function is a solution, all we can do is plug it into the differential equation and see if it works. So let's take this function and plug it into the differential equation. Well, to plug it into the differential equation, the first thing we need to do is take its derivative. So let's take the derivative of phi of x minus c with respect to x. And remember that c is a constant. So to take the derivative of this, right, we have to be a little careful. This has an inside function, which is x minus c, and an outside function, which is just phi. So we have to use the chain rule. And the chain rule says you take the derivative of the outside function, you put the inside into it, and then you multiply by the derivative of the inside function. And the inside function is x minus c. Okay, so this is phi prime of x minus c times, what is the derivative of x minus c? Well, c is a constant, so when you take a derivative, it just goes away, and the derivative of x is 1. So we get the derivative of phi of x minus c with respect to x is phi prime of x minus c. Okay, so now we know the derivative of phi of x minus c. Now we can plug everything into the differential equation to see if phi of x minus c satisfies this differential equation. So our differential equation is dy dx equals f of y. Now dy dx, remember, we're plugging our function phi of x minus c into here. So we get d phi x minus c over dx. And we want to know, is that equal to f of, the function that we're putting in here is phi of x minus c, so phi of x minus c, like that. All right. Now on the left-hand side, this is the derivative we just calculated, and it's phi prime of x minus c. And we want to know, is that equal to f of phi of x minus c? Now at this point, it seems like there's not much we have to go on because we don't really know anything about phi. But actually, we do know something about phi. Remember, phi is a solution to the original differential equation. And that means that d of phi with respect to x is equal to f of phi. Another way to write this is that phi prime of x is equal to f of phi of x. But look, this equation is true for any x. In particular, it has to be true if we replace x with x minus c, because it's true no matter what we put in here for x. So in particular, it's true for this thing to put in for x minus c. And that's exactly what this equation says. So this equation is the same as this equation, really. But this equation we've assumed to be true because we're assuming that we started with the solution phi. And so that means that phi of x minus c is a solution. Okay, so let's back up here. Remember, we started with an autonomous equation and one solution. And what we found is if you take your known solution and shift it horizontally any amount, you get another solution. So that really justifies this picture we had before where we sketched one solution, but other solutions seem to be just horizontal translations. That's actually not just approximately true, it is exactly true for every autonomous equation. If you have any solution at all to an autonomous equation, I guess for this one it would look like this. If you have any solution at all, if you just slide it sideways, you get another solution for your autonomous equation. Of course, this isn't true for non-autonomous equations, but many equations are autonomous. So this is a really nice fact about autonomous equations.